In the 1980s, at air shows around the world, the MiG-29 did something that was impossible. It slows almost to a stop mid-air, nose high, wings shuddering on the edge of stall, but then descends in a controlled leaf-like motion before recovering smoothly. No thrust vectoring, no digital flight control tricks, just aerodynamics pilot skill, and an engine that refuses to quit when airflow collapses. That maneuver was called the falling leaf maneuver, and it exists because the RD-33 survived something far more dangerous than any dogfight. The RD-33 was always a Russian engine, designed by Klimov in Leningrad. Its architecture emphasized robustness, high thrust-to-weight ratio, and tolerance to disturbed airflow. It powered an aircraft meant to fight hard, recover fast, and operate from rough conditions. That design philosophy never failed. What nearly killed the engine was not physics, but systemic collapse. When the Soviet Union dissolved, the industrial ecosystem shattered. Design authority stayed in Russia, but overall plans, tooling, trained personnel, documentation copies, and sustainment infrastructure were suddenly spread across new borders. Ukraine inherited major overall capability for many Soviet systems, not just ownership, but practical sustainment expertise built during the USSR years. For the RD-33, this fracture arrived at the worst possible moment. Early RD-33 Series 1 and 2 engines were not failing structurally. Metallurgy was sound, the disc alloys were adequate, but what limited them was life accounting. Ground running, taxi, and idle power were treated as roughly 20% equivalent damage to their fuller regimes of engine operation. The very qualities that made the RD-33 formidable in combat, rapid throttle response, tolerance to disturbed airflow, and aggressive power transients, also subjected this engine to frequent thermal cycling. Repeated transitions between idle military power and afterburner imposed steep temperature gradients in the turbine discs. These cycles accelerated creep and low cycle fatigue even when absolute temperature limits were not exceeded. Engine reached life limits early not because the materials were weak, but because accumulated thermal damage was being counted conservatively and unevenly across operating regimes. Crack initiation in turbine discs occurred long before inspections could reliably detect it, not because they were unsafe, but because the models were blind. Export fleets aged, certification paths fractured, overall authority became disputed. The engine faced extinction, not from material failure but from logistics and accounting. This is where the Phoenix moment happened. Russian engineers did not redesign the engine, they relearned it. Life tracking shifted from simple hours to damage accumulation grounded in fracture mechanics. Idle and taxi time were no longer decoupled from full power thermal stress. Partial power regimes were mapped to real temperature and strain histories instead of assumed equivalence. Inspection intervals moved closer to crack initiation physics, not just calendar guesses. Incremental metallurgical refinements followed. Not new alloy names, but improved disc cleanliness, tighter inclusion control, better forging consistency. These changes raised the crack initiation thresholds just enough for the new models to matter. Series 3 engines emerged with longer certified life, clearer inspection logic, and predictable degradation. The RD-33 did not become immortal, it became understood. That understanding is why the engine can tolerate extreme angle of attack maneuvers, airflow separation, and violent throttle transients, the exact conditions of the falling leaf. When the airflow collapses, combustion remains stable. When the pilot asks for the thrust again, the engine responds. The RD-33 did not survive because it was overbuilt. It survived because engineers learned how it actually aged. Engineering did not save this engine by making it stronger. It saved it by measuring reality and respecting it.